You are given an array of k linked lists, and each linked list is sorted in ascending order. Merge all of the linked lists into one sorted linked list. Hi, everyone. We're here today for another Exponent mock interview with Simon. For those of you who aren't already familiar with Exponent, Exponent helps you get your dream tech career with our online courses, expert coaching, peer-to-peer mock interviewing platform, and interview question database. Check it out at tryexponent.com. All right, thanks so much for being here with us today, Simon. Would you quickly introduce yourself for our viewers?
Sure. So hi, everyone. My name is Simon Ayzman, and I'm currently a senior software engineer at Spotify, working on a full stack ad tech product. And prior to my current role, I received an MBA and a master's in computer science from the University of Chicago. And in the past, I've worked as an engineer at Etsy, Bloomberg, and Foursquare. And I'm excited to be here.
Awesome. It's really great to have you here today.
Thank you.
So let's get right into it. So the question today is, you are given an array of k linked lists, and each linked list is sorted in ascending order. Merge all of the linked lists into one sorted linked list.
Could we maybe have an example of what the input looks like just a sample set of linked lists?
Okay, so let's say that in your input, you have 3 separate linked lists.
Okay.
You have 1 to 4 to 5. You have 1 to 3 to 4, and you also have 2 to 6. So then your output would probably be, you start with the 1s, then you have a 2, 3, there are 2 4s, a 5, and a 6.
Right.
Does that make sense?
Yeah, that makes sense. I guess one question I have is, can we assume that all the inputs here are well formed? Or I guess to put it differently, could I have potentially null lists inside of this input?
Yeah, you might have null lists.
Got it. Okay, so we'll probably need to take care of that when we get to the implementation.
Yeah, definitely.
Yeah, I guess another question I have is, I noticed that in this input, you have sort of like duplicate values here. One question I'd have about that is, does the relative ordering of the nodes sort of matter when the node values are equal? So basically, for example, would I take a node from an earlier list if it's the same?
Nope, doesn't matter. Either one is fine.
Got it. Okay. All right. So in which case I think that gives me a basic idea of maybe how I'd approach it. There's definitely a brute force I think of that comes to mind first. The fact that it is a series of linked lists kind of complicates it maybe a little bit for the brute force versus if I had maybe the data in arrays, for example.
Yeah.
But one brute force approach that kind of comes to mind is I could basically take all the numbers, put them inside one sort of larger non-linked list, sort that list, and then basically build a new linked list out of that.
Okay. Yeah, that makes sense. So what would the runtime for something like that be?
Yeah. So unfortunately, the runtime of that would be something like O of n log n, because we're basically sorting on n elements, where n is sort of the number of all the elements in the list. But that sort of seems a little slow given what the nature of the problem looks like.
Yeah. So do you think that you might be able to improve upon that then?
Yeah, I think we probably could. One thing that maybe I'd ask again to clarify is it okay if we modify the input lists, or am I sort of required to build an entirely new linked list?
Yeah, you can modify the input list if you'd like.
So let's take a look at the input. Maybe we can sort of get some ideas for how to improve this. So if I sort of have these as my inputs, I mean, one thing I sort of noticed right off the bat that's useful for us, I think, is that all of the lists themselves are in sorted order.
Yes,
so
exactly.
The benefit of that, I think, is we sort of have already a look into what the candidates are to start us off in this sorted linked list. It sort of gives us the next smallest values, because as we can see with this example, it's sort of at the front of each of the lists.
Right.
So I guess maybe one thing that kind of comes to mind is, I start with the front nodes of each list. I sort of like keep track of where I am inside of each list.
Mhm.
Then I figure out what the smallest one of those 3 current nodes are. And then I sort of attach it to some sort of like a result list. And I just have to make sure to keep track of the nodes in each list as I go. And we basically repeat the operation until we run out of nodes. So for example, if I kind of had this as a starting example, let's say like here I have some pointers for where I am inside of the list. I sort of evaluate what's the smallest one out of all these. So it's 1, 1, 2. Let's say the first one is the smallest. So I kind of add that to my list. And then I move over the pointer inside of that linked list. Then I evaluate again, what's the smallest node inside of these pointed 2 nodes. And again, it's the 1 inside of the second list. So then that gives us the next node. Then that moves forward. And then we do the same operation again. So 2 would be the smallest out of these three nodes. So that gives us here, and then so on and so forth. We just kind of have to make sure that we take care of the case where we sort of end the list early, perhaps, to make sure that we're not going back over these sort of null nodes. But essentially, like that can give us a fully sorted list.
Yeah, that makes a lot of sense. So now how complex is this?
Yeah, so we have to go over the nodes at least once. So I think that would be minimum O of n, but if we have something like k lists, then it would be something like O of n times k, because we have to sort of iterate through all of the nodes. And then at each of those stages, we have to determine what the smallest front node is, which is k. So it'd be O of n times k.
Yeah, because you're comparing the head nodes for k different lists at each step. So
right, exactly.
So does that seem like the most efficient way to deal with that?
We can still leverage the fact that they're sorted, but let's sort of think through what the steps are here. So we track each list or each node in the list. We for each node, or basically we iterate over each node, and then we determine, find the minimum element out of all k lists. So it'd be something like that. But that's still O of n times k. Is there something here we could potentially improve? I guess one thing that comes to mind is that when we find the minimum, we sort of keep going back over the same nodes in some sense. So like, for example, when we sort of started off, we were kind of checking 1, 1, 2. And then when we moved over this 1 ahead, we kind of keep going over some of the same elements that we had before.
Yeah.
So maybe we can improve that. Yeah, so I think actually a new approach is kind of coming to mind where maybe we can use something like a priority queue to improve this. Since at each step we're kind of going over the same elements, what we could do is we can kind of keep track of the minimums as we go, and at each iteration we basically reinsert the new node that we have, but we can still sort of get the smallest node that we have at any given time. And I think the improvement there is, so long as we keep the size of the priority queue, the size of the number of the lists, so k lists, we can improve the time complexity to n times log k. So we'll ensure that the priority queue size never exceeds k.
Right, that makes sense, especially because that means that then for any pair of nodes that you see, once you've compared them once, then they're stored that way in the priority queue, so you don't have to compare them again, right?
Right, exactly.
Yeah, awesome. Okay, so that approach sounds really good to me.
Great. All right, let's implement something.
Yeah.
So do you have like a basis for what the list node class looks like? I mean, it probably has like a next pointer and like a value. Do we have some access to something like that?
Yeah, so you can either write your own, or I can copy something over for you. You can just assume that like it just stores a value and a pointer to the next node.
Okay, great. So we'll just reintroduce it in later in case we need to in case we need to use it, but it'll be something like it'll have a value, and a next pointer, like you mentioned.
Yep.
All right, so merge k lists. So basically what we have is the input, which would basically be a series of lists. So something like this. I guess just so we kind of have our ducks in a row, we have to take care of the situation where maybe it's empty. So if the length of the lists equals 0, then we simply return none, I suppose, right? That'd be fair. We kind of want to keep track of that. Something else we need to do is we need a new head. So that'd be the new head of our final list. We can initialize that to be none. I guess we'd have to probably initialize our priority queue, right? So PQ equals Q dot priority queue. Let's make sure to import that appropriately. Great. And now we actually have to populate it. So the first thing we do is for list head lists, we have to do something like PQ dot put. We want these properly sorted. So I'm going to put a tuple essentially. So our entry will be something like the list head value. And we want to keep track of the node itself. So what we can do is put the node itself with us as we go. And then essentially we just put this inside. So that sort of starts us off with where we are inside of the priority queue. And now we just have to kind of go over the entries and make sure we kind of keep going forward in the priority queue. So while the priority queue is not empty, while it's not empty, we get the entry. So it would be node value, node, pq.get. We can sort of start to initialize ourselves properly. So what we actually should probably do is we should also keep track of where we are in the result list. So we actually probably want another node. We can start that off as none as well. And just for readability, I'll actually probably put these together. Right, so we have something like this. What we want to do is we basically want to take that and append it to our resulting list. Now we already know at this point that this gives us the minimum value node. So that's good. And like you mentioned before, we don't need to keep track of the relative ordering. So we kind of don't need to take care of that case. If maybe we wanted to keep track of the relative ordering, I may have added like an index or something here that can help us keep track of the nodes. But since that's not the case, we don't really need to do that. So one thing that I want to do here is basically if our new head is none, right, that tells us that we haven't yet initialized the list. And if we haven't yet initialized the list, then we actually have to sort of, create that new node essentially. So we would do something like new head equals node, and we have to do something similar to this. So that kind of keeps track of where we are.
In the list, right?
Yeah, and the resulting list. And just to kind of make that clear as to what we're doing, we kind of return the new head at the end.
Yep, okay.
So
new head always points to the beginning of the result list, and current node always points to the end of the result list.
Yes, like the current end, essentially, yeah.
Okay.
Now we're back to this case. So if the new head is not none, then what we basically have to do is we have to set current node's next to be the node's next value. So what that tells us is that current node dot next equals maybe node dot next. I think we may need to change that a little bit, or yeah, we may need to change that, but then we have to just make sure that we move forward in the list. So that would just be node, right? So that kind of tells us like where we are inside of our resultant list. Now, we may actually need to do a little bit more logic here because it might give us like a null pointer exception, or basically a none doesn't have a next sort of error.
I was
Yep.
also wondering, why are we setting the next value of the result list to the next of like this current node? Because it might be something else in the priority queue should be the next one, right?
Right, exactly. I guess what we haven't done yet though is that, well, at this point, we kind of had the minimum value node. So we kind of know that whatever we had previously, we're currently putting the next smallest node next to it.
Yep.
So this kind of gets us to the very end of the list. But actually, one thing that we're not doing here though is that we're not actually adding to our priority queue, because that's also something that we want to do.
Yep.
So actually, what I'll do is I'll kind of make it a little nicer. So I'll do next node is node.next. And what we want to make sure is that that's actually not none, right? We want to make sure that it's good for us to use. So if next node is not none, then what we do here is we basically figure out what the next value is. So we have a new entry here, and our new entry would be next node.val and next node. And then we put the entry inside of the priority queue itself. And I think overall, that looks good to me. Let's take a look at this. Well, I mean, one thing that sort of comes to mind is like, if I wanted to test this, like to make sure it's right, I'd probably start to write unit tests right around now, or have some sort of example scenarios to make sure that the code works. And we definitely want to include corner cases there. So I actually now, you mentioned at the beginning that we can have like the input is not always well formed. So it might be none sometimes. And I actually don't take care of that situation up here when I initialize it. So let's actually just make sure that that's valid. So if list head is not none, then we can do all that. And that actually helps us avoid some cases.
Yeah.
So this resolves that situation. Maybe let's write like a function that kind of helps us test this.
Yes. I would love to see you run the code on some test cases.
Yeah, for sure. So if we want to run the code, then we should initialize a list node class. So let's do that. So that kind of helps us there. If we wanted to write a unit test framework, why don't we start with the example that we had at the very outset, where we had like 1 points to 2. We can kind of probably re-replicate it again, but it's like 1 points to 2, points to 4, points to 6, or something like that. So list 1 equals list node. We can do it 1 and then none. Actually, why don't we be recursive about it? Like, it can kind of help us be a little clearer as to which list is which. So 1, let's say 4, 6, and then we just write none. So that's our first list. And just for argument's sake, let's also add a none case in there where it just list 4 equals none, just to make sure that we're kind of keeping our bases covered.
Yeah, I'm glad that you're testing the corner cases.
Yeah, and if I wanted to have like a more robust set of unit tests, like I would have a completely empty case, a case where it was just all none, something like that. But just to make sure that the core of our code works, like we'd probably want to test something like this. So we want to merge k lists, and we do list 1, list 2, list 3, list 4. And that gives us basically the merged head. And we're just going to have some testing code here where we kind of iterate through it and maybe print the value. So current node is merged head, while current node is not none. I'm going to iterate forward. And then all we can do is just print. So it would be something like per node dot val, and then just to make it pretty, we'll sort of add an arrow with a space.
Great.
Not supported. Yes. Okay. So basically, the issue that it's talking about here is the fact that our list nodes can't be properly compared when we're sort of keeping nodes in there.
Yeah.
So even though we're sort of comparing the values, there are a couple of ways we can deal with this. Maybe we might say that it's on purpose that this is the case, and we should actually only be storing values inside of our priority queue, and we can sort of regenerate the list if we want. But I'll actually maybe implement something here inside of the list node that basically makes it okay for us to compare list node values. So it would be something like the equality operator, would be self and other. And basically what we're sort of doing here is we want to compare, let's say just the values for now. So something like self, returns self.val equals other.val, just for simplicity's sake. And we want to kind of do something similar for the less than case, because that's kind of, it's probably going to yell at us about that too. So I think this should do it.
Okay, perfect. Yeah, that looks great to me.
All right, so let's run it again. Yes, it sort of gives it to us as sort of like a new series of lists. So what we want to do here is maybe instead of printing, actually this might be okay because this kind of still tells us what the next node in the list is. But one thing that I notice here is that the 1, the 3, and the 6, it's sort of like not quite giving us what we want.
Yeah, I think it's skipping every other one. And I think the reason for that might be the way that you've like set the next node for the so like on line 41.
Yeah.
Yeah, at the end you've set the next node to be you're skipping.
Yeah,
node.
exactly.
Yeah.
Yeah, so that was like the one thing that we ended up skipping. Yeah, this is what you brought up earlier when you said that I was kind of saying it incorrectly, but I didn't quite take that hint. So I appreciate that. Thank you. So let's try it again. Let's see if it kind of gives us a completely merged list. All right, great. So 1 to 1 to 2, 3, 4, 4, 6, 7. Great. So this looks like it works.
Yeah.
We can probably write more unit tests if we'd like, but I think this probably covers the bulk of cases, and it doesn't have a null pointer exception, so that's good.
Okay, awesome. Yeah, so thanks so much for joining us for this interview. You did a fantastic job. So I think this is a good place for us to pause and analyze the interview a little bit. What do you think went well for you in this interview, and what would you want to improve on?
Yeah, I think one of the things is that I started by sort of giving a brute force approach to solve the problem, and there's nothing inherently wrong with that, maybe, but kind of my next step after that was I didn't quite get to a fully performance solution. We sort of kind of had a little bit more of an improvement, but it wasn't quite the best. But thankfully, we sort of went through some of the examples, and I think that kind of helped us see what we could potentially improve on. Specifically, in our case, it was finding the minimum. So maybe getting to that step a little bit faster and intuiting that maybe using a priority queue would have helped us a little sooner would have been better. Another thing that I probably could have done better is that I did still have some corner cases that weren't quite accurate. I wasn't traversing accurately, like you mentioned, on line 41 correctly. So that was something I probably could have caught a little bit earlier. But maybe what was good, though, is that there were still some other corner cases that I did catch while I was going through the code and kind of tracing through it when it was basically done. So for example, when the list node is none, we probably don't actually want to add that to the priority queue. That will probably break our code.
Yeah. Yeah, I agree with a lot of those points. And you mostly focused on things that you could improve on, but I thought that there was plenty that you did really well also. So for example, I actually really like that you started off with the brute force solution and like logicked your way to the more optimal solution, because at each stage, you were able to identify what was inefficient about the previous solution. So for example, like you mentioned that we should take advantage of the structure in the input. So specifically the fact that the linked lists that you get are ordered. Whenever you get any sort of structure like that in the input, you should always take advantage of it, right? So I really like that you explicitly mentioned that. And then also you identify the inefficiency where you're comparing pairs of nodes like multiple times. So that's like redundant, right? And I think that like it often helps to start out with a brute force solution and then like logic your way to the more optimal solution. Because if you start out right away with trying to jump immediately to the smartest solution, it's much harder to immediately get that without sort of like building up the building blocks to get there, you know?
Yeah, sort of overcomplicate it ahead of time.
Exactly, yeah. And there were a bunch of things I also really liked, like you worked through examples as you were talking through your solution, you explained what each line of code did, and you had really on-point runtime analysis, and you explained how you derive the runtime analysis as well. And I thought that was all really fantastic. And so I also agree about your point that like, I think maybe the reason that you might have made a mistake on line 41 was that like the variable was named current node. So like that implies like current node, and it's a little confusing. So I think sometimes when you're working with really confusing code like this, it helps to, you know, use really clear variable names and be clear on like what each line of code is doing, you know, but otherwise like you caught the rest of your bugs as you were coding and with your test cases as well. So everything went really well.
Thank you so much. Really appreciate it.
Yeah, so thank you for joining us today, and thanks everybody for watching. If you have an upcoming interview, good luck. Thanks everyone. Bye.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video was valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching and good luck on your upcoming interview.